welcome back to my YouTube channel. So let's go to the first hybridization. First one is the sp. So in this example, we have beryllium dichloride which has an sp hybrid orbitals. So how to predict this hybridization? Okay, first thing first, okay, you need to focus on the central atom. Okay, so the beryllium chloride here, this is the BeCl2. Okay, then we need to determine which one will be the central atom. So the least electronegative atom will be the central atom. So in this case, we have beryllium surrounded by 2 chloride here. Okay, so first, okay, other than this, you need to make sure that you have the correct number of atoms. So we have here, right? So this is the Lewis structure for beryllium. Okay, so here beryllium. Okay, so beryllium, we have 4 proton number of beryllium with 1s2, 2s2 electron configuration. Okay, right? So if you look at this, okay, structure, it will give us linear, okay, linear geometry. Okay, so usually linear will give us the sp hybridization. Okay, so here you need to determine which one is the valence electron for the beryllium. Okay, so in this case, the 2s2 will be the valence electron. Okay, so first thing, alright, other than you determine the electron configuration, you need to have the 2s with 2 electrons here. Okay, and then, okay, after the 2s, we are going to have the 2p. Okay, 0, 2p, okay, or 2p0 here. Alright, so this is the s orbital, this is the s, while for the p, okay, p, it is actually located in the group 17, so it will be having the p orbital. Okay, it will be having the p orbital. So here, right, okay, so what happened here, okay, when this overlapping of orbitals between s and p, they will be what we call excitation of electron. Okay, so this one electron from the 2s will excite, and then will excite to the higher, which is the 2p. Alright, so what happened here? Okay, so excite to this orbital, and what happened here, we have, right, 1 electron at 2s and 1 electron at 2p. Okay, with 2 empty p orbitals. Okay, so this is actually from the s and this is from the p, while this is p and also p. Right, so here, right, so when we have this kind of, okay, then don't forget the energy. Okay, so what do we have here? We have combination of s and also p. So this is actually combination s and p, and this is also s and also p. So for the sp hybrid orbitals in gaseous beryllium chloride, okay, so this is what happened. Okay, this is where we have the overlapping of the s, okay, here, alright, from the beryllium itself, okay, with the p orbital, alright, here. So with the p orbital from the chlorine. Okay, so do you still remember the shape of s? Okay, so we have s, p, d, and also spd, and also f, and so on. Alright, so the shape of the s is like this. Okay, while for the p, we have 3 orbitals. Okay, we have 1 orbital for s, okay, with 1 shape. p, we have 3 orbitals, okay, which is the px, okay, py, and also the pz. alright, and the D, we have 5 orbitals here, okay, the dxy, dyz, dxz, dx squared minus y squared, and dz squared, if you still remember. Okay, so for the P, we have 3 shapes of the P. So the 3px will be like this, while for the 3py will be like this, while for the 3pz or the pz orbital will be like this. Okay, so this is the x, this is the y, and this is the z. Okay, this is the y, okay, axis, and this is x axis. Alright, so here, okay, so this is the diagram of the orbitals, okay, overlapping between beryllium and also chlorine. Okay, then we go to the sp2. Okay, so for the sp2, we have boron trifluoride, Bf3. So the boron, Bf3. So first thing, as usual, okay, please you will need to sketch the Lewis structure for the beryllium trifluoride, okay, with this structure. So if you look at this structure, it will give you the trigonal pana, okay, the trigonal pana. So for the boron, we have 5, okay, proton number. So it will give us with 1s2, 2s2, and also 2p1. Okay, so this is the first step. Second step, alright, and then you need to determine which one is the valence electron for the boron. So here we have 2s2 and 2p1. Alright, so you need to show this valence electron, right? So you need to have the energy, okay, the 2s, the 2p, okay, right. So the electrons that you need to have in 2s is 2, while for the 2p1 we're gonna have 1. Okay, right. So here, okay, this is where we have the p orbitals. Alright, so this is actually the overlapping between s and also p, also s and also p. So what happened here, okay, in order to form or in order to have a bond, a new bond, the formation of new bond, we must have an excitation of electrons. So this fully filled 2s2, one of these will jump to the higher orbital. Okay, so what happened here, we are going to have 1, okay, so this is s, this is p. So how many? 1, 2, 3, 4. So we need to have 4 here. Okay, 1, 2, 3, 4. Okay, so this is another p. So this is where we can write it down as mix or hybrid. Okay, hybrid. So one here, another one at the 2p, and another one here will be also in the 2p. Okay, so with one empty p. Okay, so combination between s and p, they will form s and p2. Okay, so this is all sp2, this is also sp2, and this is also sp2. Okay, so what happened to this empty p? So it will become the p here. Okay, if you look at carefully here, this is the empty p. What happened to this empty p orbital? So this is, if you look at carefully, okay, the 2p here, okay, the grey one here is actually the empty p with no bonding or no formation of bond. Okay, so here we are going to have one sigma, and then another second one, and the third one here. So how many orbitals, okay, do we need to have here? 1, 2, 3. Please double confirm with 1, 2, and also 3. So this is the hybrid orbitals for sp2.